Okay, let's resume. Again, I'm going to ask you to turn your cameras on, if possible. Thank you, Timur and Emre. I appreciate it. Oh, now, are there any questions about what we covered last time? Is there anything that you want me to go over again, or anything like that? Now, this might be, already familiar from high school stuff, but if there is any conceptual difficulty, do not think that, okay, I didn't understand here, but I'm going to go home, and you might be already home, but I'm going to go back and look at this again, and I'll figure it out. Let's try to figure it out here. Okay? It's much better to figure it out here. And for that to be effective, of course, you'll need to read before you come. But yeah, so I know it's not practical. I've been a student as well. I know it doesn't work that way. Any questions? Okay. Well, let's pick up with where I left off the last time with a conceptual example from the book. So this is example 21-1. So by the way, I didn't explicitly mention this, but you should have your books around because I will refer to the book from time to time for these examples and no questions, things like that. So this example is about which charge exerts the greater force. They're telling us that there are two positive point charges, Q1, which is 50 microcoulombs, and Q2, which is 1 microcoulomb, separated by a distance L. And they actually even give you a figure. And they're asking which is larger in magnitude, the force Q1 exerts on Q2 or the force Q2 exerts on Q1. And then do this explicitly. Okay? Two charges, they are of different magnitudes. They differ by a factor of 50. And they're separated by some distance. That's obviously is not very important. And they explicitly write these two forces. The force on the first charge by the second one, and the force on the second charge by the first one. And this one is going to be K Q1 Q2 by R squared. This is going to be K Q2 Q1 by R squared. And obviously, because multiplication is commutative, these are going to be equal to each other. Okay? That's just trying to reinforce the concept that Newton's third law, action and reaction, is actually applicable to electrostatics. It's not applicable everywhere. As I said, this semester, we are going to see some situations where action and reaction is not going to be applicable. And there's a way around this. This doesn't violate any fundamental laws of physics, but we'll cross that bridge when we come to it. So you can show this explicitly that in electrostatics, action and reaction principle is going to hold. Right? And it doesn't matter what this denominator is, doesn't matter what this constant is, it's just going to be the same for these two charges. Now, as I said, Coulomb's law is a vector form. Right? So how do you deal with this? Like if there are multiple charges and if there are multiple forces acting on a charge that's coming from multiple charges, then you need to be able to make a vector summation. And one way to do the vector summation is to find the forces components. Okay? And you can divide this into components, and you can just deal with this that way. Sometimes you can also use geometry, right? So I mean, I don't know if this is necessary or not, but if you have two vectors, A and say B, you can add and subtract these either by dividing them into components. So the x component of, for example, A plus B is going to be the x component of A plus the x component of B. Okay? Or you can do it geometrically. Okay? If you know the geometry, because like these are on the sides of an equilateral triangle or a square or something like this, you can actually add these guys. And that's going to be A plus B. And likewise, you can subtract them. Now, again, this is something you hopefully know, but if you don't know this, if you are having difficulty with dealing with the vectors and such, learn it now. It's already too late. You should have learned it, weeks ago. But this is how you're going to deal with this, and I'm going to show some examples regarding this. Okay? But is there anything you want me to go over about this, like when you were learning these things in calculus course or previously that something was missing that you want me to go over? Even though this is mathematics, I'm happy to repeat these things. Anything? Right. But then let's introduce a concept that you might not know from high school. Right? This is a concept that's both going to simplify our calculations, but it's also something more fundamental than the force. It turns out that nature doesn't really work with forces, it works with fields. Right? And the concept we're going to introduce is electric field. Right. Now, the proper description of the universe is using quantum mechanics. At least that's the best description that we know. And quantum mechanics always uses fields. It uses quantum fields. But this concept of electric field was invented way before this. Now, why? Why did people come up with this electric field concept? Now, the reason is that electrostatic force is very weird, just like the gravitational force. Gravitational force is also weird. Now, what makes these weird is that they're not contact forces. Right? So I'm not pushing this marker up and down, or like I'm moving it around, but I'm in contact with the marker. So it makes sense that I can apply a force to the marker. Whereas the electrostatic force between these two is action at a distance. So this F12, 1, Q2, R squared. This is action at distance, meaning the influence is not immediate. It's not just next to the object. The object that's influencing the other object is at a distance, which is somewhat hard for people to accept. In fact, Newton, when he was developing his idea of gravity, had this difficulty, and he was saying that, okay, there are some angels, pushing the planets towards the sun. And so now this conceptualization is maybe laughable for us, but this was the other one. Accepting action at a distance could take place was very hard for people to grasp. So what they come up with, what Faraday in particular came up with, is that this Q1 is producing some field, some electric field around it, and the force on this charge Q2 is coming from the interaction of the field with this charge. So there is something in contact with this charge. Okay? It's not action at a distance. The influence is not from a distance. It's actually just next to it. It's like creating some sea of influence, and when you immerse something in that sea, that you're going to get force. Yeah, so this was the idea. So the idea of electric field was invented to overcome this difficulty, the conceptual difficulty with the action at distance. But now we know that this is actually more fundamental. Now we know that this is actually a correct concept, and the fields are more fundamental than the forces. Okay, so how do you define this? Well, one way to define it is that just from what Faraday has said, the force is just going to be the charge times whatever the electric field is present. So this is the force felt by charge. This is the force, the charge feeling the force. And this is the electric field at the location of the charge. This electric field is not produced by this charge. And again, here I'm talking about the point charges. A point charge, by our definition, by our convention, does not act on itself. Okay? It's acting on by other charges, by other point charges possibly, but the point charge does not act on itself. Like an electron does not exert any force on itself. Of course, if you have a distribution of charges, then they can, parts of it can exert some force on other parts, but a point charge, by our definition, by our convention, does not exert any force on itself. So this electric field is due to the other charges. Okay? Those charges. And it leads to a force on that charge. This we're going to call our test charge. Now, why do we call this a test charge? Because it's like something hypothetical, and we're going to make this arbitrarily small. Why are we making this small? Because we don't want it to have any influence on the electric field at this location. Now, it turns out this is impossible, right? Because at its own location, no matter how small the charge is, it's going to produce an infinite electric field. If it's a point charge, you're getting arbitrarily close to the charge itself. The distance from the charge is arbitrarily small, and it's in the denominator. So it is going to have an electric field, no matter how small the charge is. But this is not a difficulty, because we are never going to encounter the situation where we need to calculate the charge at a given location of the test charge. But this test charge, we're assuming, does not exert any force on the other charges that actually produce the electric field, so it doesn't have an influence on the situation. We have some distribution of charges. These charges are in interaction with each other, they exert forces, there are other forces acting on them, and so on and so forth. But we have a given distribution of charges. And then we assume an additional hypothetical test charge that sits at various locations, and it feels the field produced by these other charges. And because of the field, it feels a force. So you can calculate the field at a given location, and from that, we can calculate the force that would be felt by a charge if it was sitting at that given location. And so this is the idea. Now you can take this and you can turn this around and write an expression for the electric field. And of course, the magnitude of the electric field is going to be the magnitude of the force divided by charge. And let's assume that there is just one additional charge, okay? Because we want to produce the electric field produced by a point charge. The force, because of the given additional charge, let's say that outside charge, charge is capital Q. Now, the force between these two charges is going to be K small q, our test charge, times the capital Q, the outer charge, divided by R squared. And I divide this out by Q. And the magnitude for the electric field I get is going to be KQ by R squared. Okay? And this is the electric field produced by Q, the capital Q, the outside charge. Field by Q. Okay? And as you see, if you come arbitrarily close to the charge, then it's going to have an arbitrarily large electric field. So there's a mathematical problem there, but we're not going to encounter this ever. Right? So don't worry about it too much. Yeah. So so I wrote the magnitudes here. So this is the magnitude of the electric field from a given point charge, the distance. But this is a vector too, right? So fundamentally, the electric field and force, they are both vectors, so they're going to have directions. And for a positive charge, the electric field is going to be outward. So if I have a plus Q, it's going to look outward like this. We are going to come to the field lines in a moment. And for negative charge, it's going to be inward. And this drawing of the field lines is a method for indicating the field that's equivalent to drawing vectors in space. And it's for some problems, for a lot of the problems that we are going to look at, it's actually more convenient. So we're going to learn about this notation. Just for now, if you're looking at a positive charge, and if you're trying to calculate the electric field at a given point, it's going to be outward from the charge. For negative charge, if you're looking at the point around it, it's going to be towards the negative charge. And you can see how this is going to be by saying that, okay, let's call this capital Q, capital minus Q. If you put a little point charge here, some little positive charge, it's going to feel a force outward. Whereas if you put a little positive point charge here, it's going to feel a force inward force charge. And so this is how you can think about this. All right. Now, not only is this useful for getting rid of the action at a distance problem, it also simplifies solving some problems. Like if you're trying to find out the force that the charge would feel because of the distribution of other charges, then it's more convenient. Now, not necessarily easier, but it's more convenient to calculate the electric field of the charge distribution, and then from that deduce the force that will be felt by this charge. Yeah? So that's what we're going to do. That we are going to be calculating the electric field given distribution of charges, and by multiplying it by the charge at a given location, we're going to calculate the force felt by that charge. Yeah? Now I want to look at some example from the book, example 21.6. I marked there. So let's see. Electric field of a single point charge. I kind of went over this already. So let's skip this one. But there's an exercise E. Yeah, this is an interesting one. So this is exercise E from page, yeah, the page is not going to be very helpful, but it's just below example 21.6. It's in section 21.6 as well. We have 4 charges of equal magnitude, but possibly different sign, that are placed on the corners of a square. What arrangement of charges will produce an electric field with the greatest magnitude at the center of square? I don't know if the question is clear, probably not from my reading, but if you're following it from the book, just below example 21.6, there's exercise E. So you have 4 charges of equal magnitude, but possibly different sign. They are placed at the corners of the square, and we're looking at the electric field at the center of the square. What arrangement of charges will produce the largest magnitude? A, all 4 positive charges. B, all 4 negative charges. C, 3 positive, 1 negative. D, 2 positive and 2 negative. E, 3 negative and 1 positive. Now, I know that while you were studying for the university entrance exam, you learned a lot of methods for eliminating the possible answers. Do not do that. Okay, forget that. It's gone. You are in the university now. There's not necessarily a single answer. Nowhere in that exercise it's saying that there's a single answer. Okay, so you can eliminate the answer saying that, okay, the magnitude of the electric field will be the same if it's all negative charges or if it's all positive charges, or if it's 3 positive, 1 negative, or 3 negative, 1 positive. Yes, so by symmetry, it can't be anything, either of those, but you can't use that. It never said that there's a single answer. Okay, and I'm saying this explicitly because I encountered this problem that we had a multiple choice in an exam, and I never said there was a single answer. And in fact, if you know the material, you will know that there are multiple correct answers. And people complained. And I said, no, this is not university entrance exam. This is not dersane. This is real life. Nobody is telling you any additional information. Unless I tell you a rule, do not assume that. Same thing goes for the exam for this course as well. Right? So you can't use elimination. You cannot say that, okay, by symmetry, it can't be A or E, or by concern. Well, how do you find this answer? So what kind of arrangement will produce the maximum magnitude when we have same charges, same magnitude charges on the corners of the square? Okay. So let's just do this as a kind of exercise. So I'm going to have plus or minus q here, plus or minus q here, plus or minus q here, and plus or minus q here. And I'm going to look at the electric field they will produce at the center of the square. Okay? Now, because it's a square, its center is going to be equidistant from all its corners. So if this distance is r, so is this distance, so is this distance, and so is this distance. Okay? They're all equidistant. So they're all going to produce an electric field magnitude. So let me be explicit that even though this is a vector, I'm calculating its magnitude. Okay, Q divided by R squared. So the electric field magnitude produced by all these are going to be the same. So I'm going to end up with vectors either like this or like that. Okay. So imagine that this is the electric field produced by this charge. Depending on its sign, if it's positive, it's going to produce the red arrow, electric field vector. If it's negative, it's going to produce the blue arrow, electric field vector. Okay. And this is true for all of them. So like in particular, this one is going to produce either an arrow like this or like that, but with the opposite sign. Okay. So this will correspond to a positive Q on the lower left corner and a negative Q on the lower left corner. The red one would correspond to a negative Q on the lower left corner. Opposite this one, and these are going to produce arrows pointing either to lower right corner or upper left corner. Yeah. So what kind of, so you have 4 possible arrows that you can produce at the center. Okay. 2 of them could be, along this line. 2 of them are going to be along this line. What's the arrangement that's going to produce the largest vector sum? So you have to draw these arrows, your vectors, and then you have to sum them as vectors, not just the magnitudes. Now, what would happen if they were all positive charge? If they were all plus Q, what kind of electric field would you produce the center?
0.
It's 0, right? They will all cancel. The electric field produced by this one will be cancelled by that one. The electric field produced by this one will be cancelled by that one. The vector sum will be 0. Same thing if they're all negative. The corner charges will cancel each other. The opposite, diagonal charges will cancel each other, and you'll get 0. Now, what would happen if you have 3 positive and 1 negative? Right? Without loss of generality, you can assume that one of these is negative, the others are positive. Now, again, there's going to be some cancellation between these two diagonal charges that are the same. Okay? Whenever you have same charges on the diagonal, there's going to be a cancellation. It's not what you want. You want them to be opposite. Right? So you can try this out, and you can figure out that if you have opposite charges on the corners, that's going to give the optimal solution, because now the electric field produced by the lower left charge minus Q is going to be enhanced, it's going to be increased, it's going to be doubled by the electric field produced by the upper right corner. And so I'm going to have a huge one like this. And so this is the sum of the electric field produced by this one and that one. And likewise, these two are going to enhance each other. In fact, they're going to double the magnitude of the electric field. And in this case, it's going to look like this. And then you can take the vector sum of this. It's going to look like that. Obviously, you can rearrange this, right? You can rotate these around, and you can have an electric field in any direction. But this turns out is going to give the largest magnitude of electric field. Now, one reason why I want to go over this example is that you have to understand the vector nature of electric field. You're doing a vector sum, and in this case, the vector sum is trivial. You can do it with geometry, but sometimes you don't have to do it with components. The second thing, just as important, is that you should not take shortcuts that you have been using, I don't know, for the last 2-3 years of your life. Okay? I know this is hard, but it's going to cause trouble. Now, when we, give assignments from the end of the book, or when we ask problems in the exam, nobody cares about the answer. Okay? I certainly don't. I mean, come on, this is a textbook, okay? We have been using this for, I don't know, maybe a decade. And we're answering questions from this textbook. Nobody cares about the answer. Everybody knows the answer. Answer is not important. You are not learning the answers. You're learning the solution, how to approach the problem. So you can actually apply this to more complicated problems. Both the general approach, how you divide the problem into smaller parts, and how you put those parts together, and also these simple concepts could be part of a larger, bigger problem that you're going to encounter. Okay? But the argument that I have seen many times when people are objecting to their exams, but I got the answer right, is not valid. Nobody cares about the answer. Answer is not important. The solution is important. And if you take some shortcut that's just valid for that problem, then that's not the solution we're asking for, right? Then you didn't learn what we needed you to learn. Okay? And then you get no points, and then there's an argument between you and the person who's replying the objections. Okay? I've seen this many times, and I don't know, maybe some professors give in, but I never gave in. Nobody cares about the answer. What's important is the solution. You have to learn this, and you have to learn this now. Otherwise, if you face the truth in third or fourth years, then you're going to be in big trouble. It's going to be way too late then. Sorry for the strength, but I do think it's important. Now let's look at a real example. Example 21.8. This is the electric field about 2-point charges. Example 21.8. Okay. Calculate the total electric field A at point A and at point B in figure 21.27 due to both charges Q1 and Q2. So I have a book here, and there's a figure 21.27, and that one has a number of charges. So there's a horizontal line. On this line, there's Q1, which is 15 microcoulombs. And there's Q2, which is minus 50 microcoulombs. And this is separated by 26 centimeters and 26 centimeters. And they're asking for this point A and this point B. And so it looks like these are just perpendicular, so I'll assume they're perpendicular. And this one is 30 centimeters. And we are to find the electric field at point A and electric field at point B. Okay. So there's some given charge configuration, and we are required to find the electric field at some 2 points given in space. The point charges, we know the electric field due to a point charge, both the magnitude and the direction. And so we can calculate the electric field separately, and we can add them up, right? When I say add them up, I mean a vector sum. We can add them as vectors. Now, just your gut feeling, which one is easier? Which one do you think is the electric field A or electric field B is going to be easier to calculate?
A.
So Timur says A. Bahar Bikman, are you with us? Okay. How about Bora Önçeken?
I think B.
You think B? Okay. Can you convince Timur? How would you convince Timur?
I don't think I can.
Okay. Is there anyone who thinks they can
Okay,
convince me?
maybe it's B because of
Oh.
the symmetry.
Sorry?
Maybe it's B because of symmetry.
Because of symmetry.
Kind
What
of
do you mean?
symmetry, a bit.
Kind of symmetry, yes.
The distance between the charges is the
Right. So
same.
this is equidistant, right? So at least the
Yes.
magnitude of electric field is going to be easier to calculate. You calculate for one, you get second one free.
Yes, but we need to add them up by vectors. Is the only
You need to
issue.
add them up by vectors, yes. But it is true that it's easier to calculate D. And symmetry is a perfect way of putting it. There's some symmetry here. Namely, if you flip this around and you split the charges, it remains the same. Right? And symmetry in physics means that when you change something, your system doesn't change, it's symmetric. Usually in everyday life, we talk about mirror symmetry. You replace left with right, you get the same thing. But there are other kinds of symmetries, like rotational symmetry, spherical symmetry, or cylindrical symmetry, things like that. So here we have a reflection charge symmetry. If you reflect this around this line and you replace minus the charge with minus charge, you get the same situation. But another way to say this is this is of equal distance. Okay? So it's going to produce the same magnitude of electric field. Now, how does this help? So let's just assume I calculated this. Okay? Can you calculate the distance from A to this point Q1, or from B to this point Q1? Is there anyone who says, oh, that's just out of my league, I can't do it? Don't say that. Okay? If the situation is described well enough, you should be able to calculate it. In this case, it's simple. You just use Pythagoras theorem. So right triangle. Okay. So it's a right triangle. You have these two right sides. The square, the sum of the square of these two right sides is going to give you the square of hypotenuse. So you can calculate it easily, okay, in centimeters or whatever. Of course, you need to convert this to meters to get your answer in newtons if you use the quoted figures for K and epsilon naught, but that's a minor difficulty. All right, so that's going to be the same for here. Okay, now what will this vector look like? What will the electric field produced by this Q1 at point B look like? It's going to be outward, right? Because positive discharge will feel a force, repelling force from this positive charge. So it's going to look like this. Right? Let's call this E1 at this point. Now, on the other hand, this one is going to feel
Inverse.
an attractive force, right? Kind of downwards, something like this.
So the y direction force will cancel out, and they will just have the force to the right.
Okay. So you say y direction, I'm going to say the vertical direction, but we can always draw a coordinate system, which we are going to need anyway, and really make this a y direction. So because these two angles are the same, the vertical components or the y components of these two vectors are going to be the equal and opposite to each other, and they're going to cancel. Now, why are these two angles the same, though? And this one is the same as that one. Yes, it's just I'm extending this. My drawing is bad, but we imagine that this is just an extension of the hypotenuse. So these two angles are the same. These parallel, this is horizontal, this is also horizontal. So these are parallels. There's a theorem, like these are parallel angles or something. Now, why are these two the same? Why is this equal to each other? Right. So let's extend this one as well. Again, my drawing is bad, but bear with me. So because this is a isosceles triangle, this angle is going to be the same. And this is a straight line cutting two parallel lines. These are interior inverse angles, I think. I don't know the English name. İç ters açılar, we call it in Turkish, but is an interior inverse angle, so they must be the same. And because these are equal to each other, these must be equal to each other. Hmm? Or it could be that you have seen this problem a million times and you already know that the angles are the same. That's how I do it. But this is the justification. So the y components are going to cancel, and x components you need to calculate only once. The electric field, the total electric field, the x component is just going to be the electric field coming from the first one plus the electric field x component coming from the second one, but they are the same. Right, so this is just twice the electric field coming from just one of them. Now let's call this angle theta. Let's give it a name. Then I can write this as twice the electric field produced by charge 1 at point P times, now I'm looking at the x component, the horizontal component, that's the adjacent component to this angle, so it must be the cosine of that angle. Okay, this is R. And I can write that cosine of that angle. The cosine of that angle the adjacent side divided by the hypotenuse. Right? In this case, 26 centimeters by whatever you find for r. Let's call this L, just for convenience. And this is going to be 2 E1 L over R. Now, what is E1? Well, that is 2 1 over 4 pi epsilon naught. Let's squeeze it here. This is 2 1 over 4 pi epsilon naught. So this A is Q1 divided by R squared L over R. Okay? And there you have it. This is the magnitude of the electric field. The electric field produced. But B is in fact electric field, the x component of the electric field, which is just what we calculate here, times x hat. Or maybe you've seen this as I hat. And it's the same thing. The unit vector in the positive x direction. All right, so this is how you handle things. But the way I solve these kind of problems is really, I don't try to substitute numbers too early. Like I could start by calculating this r, taking the square of 26 and the square of 30, adding them up and taking the square root. But you don't know if you're going to need r or r squared in the end. Maybe you're never going to need r, but just r squared, and you don't need to take the square root. Okay? So just delay things till the end, keep things as simple, and then at the very end you can substitute, whatever you want to do. Sometimes this doesn't work. Sometimes the expressions get really very, very, very messy, very hairy, and then you need to really make some substitutions early on. But this is not the case for this problem. It is for this part. Now, how about over here?
Hocam, can I ask something?
Please, by all means.
Can we also write the answer as 1 over 4 pi epsilon naught times p over r cubed?
What's P?
Dipole moment.
But we can see dipole moment, right?
Yes,
I mean,
but
you might know what dipole moment is, but we haven't covered it yet. So it's like knowing the answer, and so the dipole moment, that formula, the P that you need to calculate, this comes actually from solving this problem. Right? You have a dipole, two equal and opposite charges separated by some distance. But that's exactly the kind of things you should not do in an exam. It's a shortcut. You might know that, but it's not given. And I don't know if this is because of my experience or because of the way I think, because I'm a physicist, which is not fair to you because you're not a physicist. But when I look at this problem, it's clear to me. I'm not going to say obvious is too strong a word, but it's clear to me that they are not asking me to use the dipole moment. Right? This is a problem from this chapter. We haven't seen dipole moment yet, and I might know this, but I will never try to solve this using dipole moment. Okay? It's a shortcut, and obviously the problem is not asking for this. Again, sorry, I said obvious. It's definitely not obvious, but that's something you should not do in an exam. Try to get into the mind of the person who's asking the question. Why are they asking this question? Because they want you to use Coulomb's law and calculate the electric field for an individual charge and do a vector sum. Okay? Again, nobody's interested in this number, what this number is. Everybody knows what that is. It's an example from the book. But they want you to be able to carry out this calculation, which then you will use to get the very nice simple expression for the dipole moment, but not at this stage. Okay? I don't know if this is clear. It's especially since I'm not seeing your face, it's very hard for me to judge whether you're following or rolling your eyes or whatever. But,
yeah, it's obviously clear. Thank you for that.
Sure. Okay. How about here? How about this point A? Now you kind of proceed the same way. There is no symmetry this time. You have to calculate the magnitude of the electric field due to the first one and due to the second one separately. You need to calculate the distances. Well, in this one, the distance is given, it's 30 centimeters. In the other one, it's going to be the hypotenuse of the right triangle with the sides 30 centimeters and 52 centimeters. So you can just calculate that. And then you need to make a vector sum a little bit differently. So here, the vectors are going to look like, so this one is an outward one. And this one is going to be pointing this way. And as you see, this is smaller, right? They are no longer the same magnitude. So this is a pure, this is a vector purely in the y direction in our coordinate system. This one has two components. So you need to calculate the components of this. And this is done in the book. So I'm not going to go into the detail of this, but this is the logic. Yeah. So to calculate that one, the components, you will need like this angle, let's call this alpha. And that angle alpha is going to be same as this angle alpha. Okay. So to calculate the x component of this electric field vector, you will need cosine alpha, but cosine alpha is 52 divided by this hypotenuse. And you also need to calculate the horizontal component. For that, you'll need sine alpha, the opposite component, and that's going to be 30 divided by the hypotenuse. Yeah. So you already have this. You don't need to make anything complicated. If you calculate the hypotenuse, you can calculate the sine and cosine of this angle as a fraction. And I think in the exam, you're not allowed to use, I don't know if you're allowed to use calculators or not, but if calculators are not allowed, you can probably just leave things as they are. And these will be just symbols, and you can just leave them as symbols. Just, check this out. It's really not useful for me to go over this example, which is already solved in the book, but try to solve it on your own. If it doesn't make sense, if you can't make progress, check out the solution in the book, try to solve it again, and then come to me with a concrete question. Like when I say, do you have any questions from the assigned problems and things like that? I can't solve example 21.6 is not a question, it's a statement. I need a question to answer. I can't solve 21.6, well, too bad, okay, what can I do? But when I was trying to solve problem 21.6, I tried to calculate, this distance. How do you calculate sine alpha in this case, right? So that's the question. That's something I can answer. Calculate something concrete. You should really try to solve the problem, and stop somewhere because you can't proceed anymore. Then I can help you. If you say that I can't solve this, okay, you can't solve it. Too bad. What can I do? Be more specific, be concrete, and then I'll be able to more help you.
Hocam, may I ask?
Yeah, go ahead.
Are you on campus?
I am on campus, yes.
Yeah, okay. Can I come to your office for office hours if
I don't have office hours though. I don't have office hours.
Ah, okay. So do I need to ask first on email for appointment?
Yes, yes.
Okay,
Yes.
okay.
Yeah.
Thank you.
Right. So this is something I'm going to go into next week, but like a lot of the stuff for the electric field comes from not these single discrete point charges, but from continuous charge distribution. And this is, I'm going to make an introduction now, and I'm also going to post some videos on YouTube. A lot of the assigned problems are like this. And also, there are a lot of problems in the book that you can take a look at. But let's make an introduction. I also post the videos. You can take a look at these, and we're going to tackle this on Monday. So continuous charge distributions. Now, what do you mean by this? Well, what we mean is that really just continuous charge distribution. So you can have just points, and this will be called discrete charge distributions. Or you can have like charge smeared all over some surface or some rod. Let's say something like this. Okay. And this goes to infinity and beyond. Okay. And I try to calculate the electric field at a given point. Okay. So this is a rod that's of infinite length, but infinitesimal thickness in both directions. So it's just imagine a cylinder that's infinitely long, but with very, very, very small radius r. When I say very small, I mean it's very small with respect to the distance of this point I'm interested in from the rod itself. Okay, that's sufficient. But it's also very long. When I say very long, again, what I mean is that the length of this rod is much larger than the distance of this point at which I'm interested. Now, how would you calculate this? Okay. The way to handle that is to divide this continuous charge distribution. So this is now the charge smeared all over, and get some little part that has some charge dq in this field. Yeah, there, some dq, and this is going to lead to some dE. Okay. So I'm going to take this rod and divide this into infinitesimal parts. Each part is going to have some charge dq, and each of those dq are going to produce some electric field dE, and I'm going to vector sum all of these. Okay. Now, how does this work? Well, the relationship between E and dq is fine, but you've seen this already. Let's say this is 1 over 4 pi epsilon naught dq by r squared. This r is obviously going to depend on where you are on the rod. R is not a constant. Okay, it could be that in your problem, like one of the examples in the book, that all your points are equidistant, but not necessarily so. If they're all equidistant, then this simplifies. But that simplification might not be available. And then you're going to calculate the electric field by adding all these up. Now, there's an important point here that you need to be careful. That your electric field is going to be an integral of all the electric fields. And this integral is taken over the charge distribution, okay? Meaning that I need to have some way of going over space and covering all of these charges. Okay? So in this case, this is going to be simple. Let's say that I have a coordinate system like this, and y going from minus infinity to infinity is going to cover my infinite drop. I don't need to change anything in x, but there are more complicated situations that we're going to see. Now, this is correct. This is how you handle this. You start with an infinitesimal electric field, and you add up all of those electric fields to get your total electric field. And adding up an infinite number of infinitesimal things is called the integral. Okay? But this is not correct. Okay? It's a vector sum. Electric field's a vector. When you're adding up infinitesimal electric fields, you have to take them as vectors and take the vector sum. Now, this is not practical, right? You can't use geometry and things like that, and the magnitude of this is going to change. How do you do this? Well, you do this by dividing into components. So even though this is not correct, this is. Okay. And how do you do that? Well, this is just x component of whatever electric field that's being produced by this little charge. Okay? So to get this, the x component of the electric field, you calculate the magnitude, and then there's going to be some geometric factor. Like, for example, in this case, let's say that I'm trying to calculate it here. Okay, this is going to produce an electric field like this, and I'm going to have some angle alpha here. This is also going to be alpha. This is going to depend on my y coordinates. Okay, so like tangent alpha is going to be y over t. So I can actually figure out, given y, I can figure out what alpha is, at least in principle, or cosine of alpha or sine of alpha. And I'm going, if I'm trying to calculate the x component of this, that's the horizontal component, that's going to be dE cosine alpha. Okay, this is going to be dE cosine alpha. And as I said, given my y, I can actually figure out cosine alpha easily. In this case, it's going to be d divided by d squared plus y squared square root, d divided by the hypotenuse. Okay, but maybe we're going to go over this example explicitly. But this is the idea. Okay? This is correct. This is not. right? You can't just add up the magnitudes unless they're all in the same direction. You can't, but you can add up all the components. So what you need to do is to figure out the component using the magnitude and some geometry, and then add those up for each component. Now, like in this case, this also has symmetry. It's an up-down symmetry. So you can tell immediately, because it's up-down symmetry, the electric field is going to be horizontal. So you don't need to calculate the y component. You just need to calculate the x component. Right? Sometimes the symmetry is not going to be obvious, so you will need to explicitly calculate something, and then you'll find that it's 0. That's fine. Okay? If you can use the symmetry, use it. But saying that, oh, this is 0 by symmetry when it's not 0 is just you can't recover from it. Okay, so unless you're sure, don't be overzealous about using symmetry. As I said, this is something complicated. We are going to cover this next week. But before that, I want you to look at the section, read it. It's complicated. You can't hope to understand what I'm doing just by watching me. You have to work on your own. I'll also post some solutions on YouTube. I'll also post a document on OptiClass, so you can take a look at this. And yeah, I know it's weekend, but this is the way our schedule works. Okay? You'll need to do a little bit of reading over the weekend. Okay? I don't know your situation, maybe you can't do it, so on and so forth, but this is something that's going to regularly happen, that you're not going to get ready for a Monday lecture by doing some reading on the weekend. Okay? So try to make an arrangement for this. If you can't, you can easily guess what's coming on Monday and do it during the week. But it is necessary for you to get maximum out of these lectures to be able to prepare. Right. So that's all I want to say. Do you have any questions? Any comments? Right. Then I'll see you all on Monday. Take care. Bye.
See you, Hocam. Goodbye.
See you.